To really understand what quantum numbers are, it's important to learn both definitions and a bit of history. Firstly, what does quantum even mean? The adjective quantum, as in quantum mechanics or quantum physics, comes from the noun quantization. In short, quantization refers to the tendency for matter or energy to be grouped in set or certain quantities. An example of quantized matter is an atom. We know that each element has a certain set or quantized set of protons. There are no half protons or quarter protons, so each atom's atomic number increases by 1 with each proton added. Quantized energy, then, is energy that we know is released or absorbed in these chunks or sets. An example of quantized energy is the potential energy of electrons in an electron orbital. There are no half or quarter orbitals, and so we know that the energy given off from a certain orbital will always be the same. Think of it as energy being given off in steps, like steps on a staircase. Each step is a certain height, so you gain or release energy in relation to those steps, as opposed to gaining or releasing energy on a continuous ramp. So that's cool, but why does any of this matter? It helps us to understand very small bits of matter and energy that come from things like atoms and electrons. Through understanding quantization of energy, Max Planck, the renowned German scientist, gave a number to this quantized amount of energy with this equation. F is the frequency of an oscillating object, meaning the object absorbs and emits electromagnetic radiation of frequency F. E is the energy of that object, and the amount of energy can increase or decrease in a quantized amount, h, which happens to be Planck's constant. It's a really small number, 6.63 times 10 to the negative 34. Later, Danish scientist Niels Bohr was able to use Planck's constant to construct the model of the atom that most of us recognize today, the Bohr model. Bohr used physics alone to create equations to find the quantized angular momentum, L, of an electron in a hydrogen atom, the radius of a hydrogen atom's orbital, and the energies of electrons in a hydrogen atom. You may notice that all of these are for hydrogen atoms, and the fact is that Bohr's equations can only be used for hydrogen atoms and for nothing else. But the theory behind them was used to create what we know today as our quantum numbers. Understanding the properties of electrons helps in understanding how matter works, since atoms are the building blocks of matter. There are 4 quantized or quantum numbers which we use to describe any electron in any atom. Niels Bohr used the very first one in his equations about the hydrogen atom. This number is called the principal quantum number. It's denoted with N and describes the energy level that any electron we want to describe is at. Thinking back on Bohr's model of the atom, we can see that each of the orbitals around the nucleus can be given an energy level starting at 1. The first one, n equals 1, the second, n equals 2, and so forth. Bohr's model of the atom, however easy to remember and visualize, was incomplete, as was his understanding of quantum numbers. Arnold Sommerfeld, another renowned scientist, added another quantum number to help increase our understanding of atomic orbitals. This quantum number is called the angular momentum number, and is denoted by this fancy curly L. L can be any positive number that is n-1, or 1 less than the principal quantum number. Because we now know that atoms don't have these circular energy levels, but have complex orbital clouds, this number helps us understand what kind of cloud the electron is in. If n equals 4, L can be 0, 1, 2, or 3, and each of these corresponds to a different shape of atomic orbital. L equals 0 means an s orbital, this spherical shaped kind of cloud, and there are always only one of them per energy level. L equals 1 denotes a p orbital, which are any of these 3 dumbbell shaped clouds, which extend out in x, y, and z directions, and there are a max of 3 per energy level. L equals 2 denotes a d orbital, which are these funky looking kinds of clouds, and there are a max of 5 per energy level. Finally, L equals 3 corresponds with an f orbital, which look like these even funkier looking orbitals, and there are a max of 7 of these per energy level. How do we know which one of these kinds of orbitals the electron is in? Sommerfeld helps us with that question as well, as he also created the third quantum number, the magnetic quantum number, m sub L. M sub L describes the specific s, p, d, or f orbital that the electron is in, and can be negative L to positive L. So if we look at a p orbital, which is L equals 1, m sub L can be negative 1, 0, or 1. and each corresponds to a specific p orbital shape, as seen here. Lastly, we have the spin quantum number, m sub s. Wolfgang Pauli, George Uhlenbeck, and Samuel Goudsmit contributed to understanding that all electrons in an orbital spin around their axis. There can be only 2 electrons in each orbital cloud L, and those 2 electrons spin opposite directions, clockwise and counterclockwise. We denote this by giving m sub s equals positive 1/2 for clockwise spinning electrons, and m sub s equals negative 1/2 for counterclockwise spinning electrons. Now that we know all about how to exactly describe a specific electron in a specific orbital with a specific spin direction, this can help us understand larger properties of matter, like why atoms bond in certain ways, and the reasons for dipoles in molecules. One physics concept, which is explained by these quantum numbers, is magnetism. An atomic orbital with paired electrons is called diamagnetic and has no specific magnetic properties. These kinds of orbitals can be in anything that isn't attracted or repulsed by a magnet, like diamonds, wood, or copper. The opposite spinning electrons create opposite magnetic fields, which cancel each other out, giving no overall magnetic properties. Atoms with unpaired electrons, however, are called paramagnetic, and these do exhibit magnetic fields. Because the unpaired electron's magnetic field does not get canceled out, this field is exhibited even in large matter, like picking up iron nails with a magnet or playing with those loud things that you did when you were a kid. And there you have it. Thanks for watching.